Hello everyone, welcome back to my channel InPhuSecLab. Today we're going to talk about another vulnerability, server-side template injection. In this TryHackMe room today, we discuss what server-side template injection is and outline the basics methodology for exploiting server-side template injection vulnerabilities. We'll also suggest ways of making sure that your own use of templates don't expose you to server-side template injection. As usual, before getting to any exercise, we need to go over some basic concepts first in order to understand the vulnerabilities. Server-side template injection is a vulnerability when user input is injected into a template engine of an application. This can lead to security issues, including code execution, data exposure, privilege escalation, and denial of service. SSTI vulnerabilities are often found in web applications that use template engines to generate dynamic content and can have serious consequences if left unaddressed. A few prerequisites: basic understanding of HTML structure and how web pages are built, basic understanding of JavaScript for client-side scripting, and some familiarity with server-side programming language concepts like Python or PHP or JavaScript. Okay, first we're going to add this one to the host file. Echo 10.10.218.246. SSTI Overview. Server-side template injection is a vulnerability that occurs when user input is unsafely incorporated into the server-side template, allowing attackers to inject and execute arbitrary code on server. Template engines are commonly used in web applications to generate dynamic HTML by combining fixed templates with dynamic data. When these engines process user input without proper sanitization, they become susceptible to SSTI attacks. The core concepts of SSTI: dynamic content generation. Template engines replace placeholders with actual data, allowing applications to generate dynamic HTML pages. This process can exploit it if user inputs are not properly sanitized. When user inputs are treated as part of the template code, they can introduce harmful logic into the render output, leading to SSTI. The core of SSTI lies in the improper handling of user input within the server-side template. Template engines interpret and execute embedded expressions to generate dynamic content. If an attacker can inject malicious payloads into these expressions, they can manipulate the server-side logic and potentially execute arbitrary code. When user input is directly embedded in the templates without proper validation or escaping, attackers can grab payloads that alter the template's behavior. This can lead to various unintended server-side actions, including reading or modifying server-side files, executing system commands, accessing sensitive information. Template engines. A template engine helps build web pages dynamically. Imagine you're making a birthday card for a friend. Instead of running a new card from scratch, you use a template with a placeholder for name, age, and message. A template engine works similarly. The engine uses a pre-designed template with placeholders for dynamic content. The engine receives user input like the name, age, or message and stores it as a variable. Combination. The engine combines the template with user input, replacing placeholders with actual data. Output. The engine generates a final dynamic web page with the user's input inserted into the template. Template engines offer various functionalities that speed up development, but can also introduce risk. Most allow expressions for simple calculations or logic operations within templates. In the context of SSTI, the engine's ability to execute code makes it vulnerable to attacks. If user input is not properly sanitized, an attacker can inject malicious code, leading to unintended consequences. There are some common template engines. Template engines are an integral part of the modern web development, allowing developers to generate dynamic HTML content by combining templates with data. Here are the most commonly used templates engines. Jinja, popular in Python application. Twig, the default template engine for Symfony in PHP. PHP, known for its minimal and clean HTML templating syntax, popular among NodeJS developers. So how template engines parse and process inputs? Template engines work by parsing templates file, which contains static content mixed with special syntax for dynamic content. When rendering a template, the engine replaces dynamic parts with actual data at runtime. For example, we have this template right here, hello name. Output is hello, render the name is world. The world is the user input combined with the template to print hello world. Different template engines have distinct syntaxes and making them vulnerable to SSTI in various ways. Here's some samples of vulnerable syntaxes. Jinja and Twig. Jinja and Twig are similar in syntax and behavior, making them somewhat challenging to distinguish from each other. By just by Jinja 2 and Twig. These two are similar in syntax and behavior, making them somewhat challenging to distinguish from each other by payload responses. You can detect their presence by testing their expression handling capabilities. For example, using the vulnerable VM, if you use the payload 7, the output will be 49. However, if you use the same payload in the application that uses a Jinja 2, the output would be 7. So depending on the template engine, the output is different. PHP, formerly known as J, uses a different syntax for handling expression, which can be exploited to identify its usage. PHP evaluates JavaScript expressions with this syntax. For example, if you use the payload like this, it will return 49. And like Jinja 2 or Twig, PHP or Twig allow JavaScript execution within its templates without the need for additional delimiter like this. Okay, so this is a sample. Click it to proceed to the next task. I wanted to see some demonstrations. So let's copy this one. With PHP and PHP. Which one we have Jinja and Twig, they are similar. If you use the payload on Twig, we get 49. If we use Jinja, Jinja is for Java. We don't have Java right here. Oh, right here. We get 7 number 7s. J, the PHP is for JavaScript. We use this syntax. So we use this one in the J. Syntax is going to, I wonder what it is if we use the quotation mark right here. Still 49. Okay. All right, moving on. PHP Smarty. Smarty is a powerful template engine for PHP that enables developers to separate presentation from business logic, improving application maintainability and scalability. However, its capability to execute PHP functions within a template can expose applications to server-side template injection attacks if not securely configured. Smarty's flexibility allows for dynamic execution of PHP functions within its templates, which can become a significant security risk. The ability to execute PHP code through the template variables or modifiers should be carefully controlled to prevent unauthorized command execution. For the exploitation, let's go to this one, Smarty. inject a simple array hello to see if it would be processed. It's on 8,000. If the application returns hello, it means the template engine used by the application is Smarty. Syntax error, template hello. Got everything. I guess there's no space. There we go, no space. Once you confirm the site is vulnerable to SSTI via Smarty, you can grab a payload that uses PHP function that executes system commands. One of the most common functions to do this is system function, using the payload system ls. Let's try that. System ls. Okay, so we got a text file right here. Using the payload, do we include everything? What? We have 2 flags? Okay. When a Smarty template engine process input, it will execute the else command. This command will reveal the directory listing of the server directory when the script is executed, providing insights into the server file system. We have 2 files. Why am I getting 2? Oh, it prints out twice. My bad. I thought there were 2 flags. NodeJS, PHP, formerly known as J, is a high-performance template engine widely used in Node.js community for its concise HTML rendering and advanced features like conditionals, iterations, and template inheritance. While PHP provides powerful tools for developers, its ability to execute JavaScript code directly within the template can pose significant security risks. PHP security's vulnerabilities stem from its capability to interpolate JavaScript within the template variables. This feature for dynamic content generation can be exploited if user input are embedded without proper sanitization. Developers must diligently sanitize and validate user input to ensure and key vulnerability points. So, JavaScript interpolation. PHP allows embedded JavaScript within templates using interpolation braces. If user input is interpolated without proper sanitization, it can lead to arbitrary code execution. Default escaping. PHP does provide automatic escaping for certain inputs, converting characters like greater sign, smaller size, and ampersand to the HTML entity equivalent to prevent access attacks. Default behavior does not cover all potential security issues, particularly when dealing with unescaped interpolation, like the exclamation mark with the braces, or complex input scenarios. Select. Let's see. Let's explore this one. Jade. Inject a basic PHP system. Syntax to test template processing. We tried that earlier, and then it was returning 49. In the application output 49, it confirms the PHP is processing the template. Since PHP allows JavaScript interpolation, we can use the payload root process main modules. Okay, let's break it down. The root.process accesses the global process object from Node.js within the puck template main module that dynamically requires the child process module, bypassing potential restrictions that might prevent its regular inclusion. Spawn sync ls execute the ls command synchronously, and state the output capture the standard output of the command, which includes the directory listing. Oh no. What? Did I miss something? This is J, right? Yeah. So now we can change this one to cat and using this file name. Huh. Doesn't show anything. Why spawn sync lslah may not work? When you try to use a command like this, you are attempting to pass the entire command and its argument as a string. This does not work as expected because the spawn sync does not inherently split single string into a command and its arguments. Instead, it treats the whole string as a command to execute, which it cannot find. Okay, that's why my cat command was failing. This behavior is critical for preventing security vulnerabilities such as command injection, where an attacker might try to append additional command or arguments to execute unintended actions. Understanding the spawn sync usage. The spawn sync function is designed to execute a command in a shell and provide detailed control over the command's input and output. It's part of Node.js child process module, which allows Node.js to execute all the processes on the system where it runs. The function signature for the spawn sync. So this is going to be usage of that function. The command is going to be the name of the command, arguments, and options. Instead of running the command like this, we have to cat, and then this one is going to be another parameter. Argument. Let's try that. What? Oh, it has to be in the bracket, in a square bracket. Okay. I see, because there can be multiple arguments. Understood. There we go. And we got the flag. So as you can see right here, ls, the first one is the command. I used cat and then the name of the file. This command only requires one argument, but for several other commands like ls, it has multiple arguments like lsl, ah. We can put them all into this array. Okay, this structure ensures that the ls command is called with lah as its argument, allowing the command to function as intended. The final payload would be something like this. And we were able to retrieve the content of the flag. Moving on, Jinja 2. Jinja is a popular template engine for Python, renowned for its flexibility and performance. It is extensively used in web applications to render dynamic content, as it allows Python-like expressions to be embedded within the HTML. While Jinja 2 accelerates the development and facilitates the separations of presentation from business logic, its powerful template capabilities introduce significant security risks if not handled properly. Since Jinja 2 allows the execution of Python expressions within the templates, the security risk in Jinja 2 often arises from insecure coding practices that allow user input to be executed within templates without proper sanitization. The vulnerability is not inherent in Jinja 2, but in how developers handle user inputs. Properly sanitizing and validating user inputs before incorporating them into templates is essential to prevent security issues. Jinja 2 evaluates expressions with the curly braces, which can execute arbitrary Python code if crafted maliciously. Advanced features like template inheritance and macro imports can be misused to execute unintended code, leading to information disclosure or server manipulation. Before crafting a payload, confirm that the application uses Jinja 2. 7 times 7 should be 49. This is an indication the machine is running Jinja 2. Once confirmed, use a payload. Below is a breakdown of the payload. Access is the base object class, the superclass of all Python classes, okay? Subclasses of the object. And 157 is typically the index of the subprocess.popen. This index may vary and should be checked with the target environment. We have to determine the index value. Let's try that. Class, no, stop here. Subclass, we have an extra parenthesis. What are we looking for? The popen class, subprocess of popen. Showing subprocess. What did I do wrong? Class MRO, one subclass. So the payload is correct. Subprocess popen. Subprocess popen. Interesting, it's not showing right here. Okay, let's continue reading and see what we can figure out. The subsequent method changes dynamically import and use a subprocess module to execute various command, capturing its output. Can we try the whole thing right here? Does it work? It works, okay. The subsequent method, okay, we're here. So check what you use ls, you're passing entire command and its argument as a single string. So similar to pub, when you input this whole string, it will be treated as a single string, not a command with its arguments. So we have to pass in the command name and the argument itself. Right, we have to modify our command, put them in an array. First is the command name, second is the file name, copy the whole thing, paste. We got a flag. Moving on to automation tools. SSTI map testing and exploiting SSTI vulnerabilities in template engines on Hub. It provides a framework for discovering template injection flaws. So if we use the attack box, it's in opt SSTI map directory. If we're using our own machine, you can install it by cloning the repository. Okay. SSTI is capable of the template engine detection. The map can identify the template engine used, crucial for crafting specific exploits. Automated exploitation. For known vulnerabilities, SSTI map can automate the process of exploiting them. You can use SSTI map by providing the target URL and any necessary options. And we ran the tools and found shell command execution reverse shell file read. We got several injection points. So this is the basic use of SSTI map. If you're interested, dive deep and see what it does. This is just an introduction. Tools are helpful, but manually exploit the vulnerability first. Okay, challenges. Another web app is running on port 8080. Can you achieve the RCE and read the header file? Since start, win. This is from right here. I'm gonna do some reconnaissance when I first get on the form tools. I have the version number. There's an update button. Seems like it's using an old version. Doing some Google search, I find there are some vulnerabilities, especially SSTI, of these specific form tools. I see server-side template injection vulnerability is present in this version 3.1. So we got this one right here. It's vulnerable. Allows attackers to run arbitrary commands by the group name field under the app form section of the application. The group name field. Let's try adding. Where's the group name field? Oh, right here. Add new group. Create a group. Update. S49. This is the injection point right here. Going back to the room, if you remember, Jinja and Twig use the same syntax. Jinja 2 and Twig are similar in syntax and behavior. When you try to send payload, depending on the output, we can determine the engine template. Since we tried 7 multiplied by 7 and the output was 49, we can confirm that it's using Twig. Because if we were using Jinja 2, the output was going to be 7 number 7s. All right. As you can see right here, output is 49, so that's Twig. And we know that Twig is used on PHP server. Another indicator is right here. You look at the URL. The extension is PHP, so we know it's using PHP. Because of that, we can use some PHP command to run the OS commands. Let's try system ls. We got the directories right here. But I'm going to see this in burp suite because it's hard to see the contents of the output. So let's use burp suite right here. Intercepts traffic. Going back to the application. Let's try one more time. Burp sound. System. Okay, it's capturing burp suite. Send it to repeat. Where was LS? LS right here. Send it. And where we're looking at the response, the view group. View group. One, two, three. It's going to be the second match. And we see the content of the directory. When you look at the payload, it seems like everything is encoded. So I'm going to use CyberChef to encode the payload before sending it to the server. URL code. Where was the flag? The hidden text file in the directory SSTI. First, let's see where are we right now. We are currently at the edit. We have to go back. This is the server directory. var www.html. This is always the server directory. All right. So ls la. We have to encode everything. System. It's a little bit hard to see right here. Hopefully it works. There we go. It works. What do we have here? Forgot password. We have the hit text file. So copy. Now change the command to cat. Again, code everything. And we got the flag. All right, we completed the challenge. On the real world example, the same approach should be done. First, when you get on the application, look up the version of the service it's using. We have all the information of the service we're using. We can perform a Google search. I search the SSTI, but usually I just search vulnerabilities. And Google is going to give you a list of all the known vulnerabilities related to this specific version. From there, we can read whatever we're trying to exploit. Since we're doing SSTI, we're only interested in the vulnerabilities that has to do with SSTI. But you get the concept. Once you take a look, you know the injection points, because otherwise we'll be wasting a lot of time, trying to figure out the injection point. Over here is one point, and then if you take a look at right here, we got the fields right here. These are all injectable. Even like when I first tried to create a form right here, this one can also be injected. I don't know. It may be not, but we have to go through each of the input fields and try each of them, which is time consuming. All right, let's talk about mitigation. Server-side template injection can be mitigated by best practices and security measures in the code. Here's how to mitigate SSTI. For Jinja, enable the sandbox environment in Jinja 2 to restrict the template ability to access unsafe functions and attributes. This prevents the execution of arbitrary Python code. Input sanitization. Always sanitize input to escape or remove potentially dangerous characters, strings, and interpreted code. Template auditing. Regular review or audit templates for insecure coding patterns, such as that directly embedded user input without sanitization. Shade. Avoid direct JavaScript evaluation. Restrict using Puck's ability to evaluate JavaScript code within the templates. Use alternative methods to handle dynamic content that do not involve direct code execution. Okay. Validate and sanitize input all the times. For any kind of injection vulnerabilities, we have to validate and sanitize input. Secure configuration setting. Use environment settings and configurations options that minimize risk, such as disabling features that allow script execution. Smarty. We disable the PHP tags. Ensure PHP tags are disabled in Smarty configurations to prevent execution of PHP code within the templates. Use secure handler. If a user customize templates, provide a secure set of tags or modifiers that do not allow direct command execution and shell access. Regular security reviews. Conduct security reviews of template files. and data handling logic to ensure no unsafe practices are being used. Regular updates Smarty to keep up with security patches. Sandboxing in the template engines is a security feature that restricts the execution of potentially harmful code within the templates. It limits the actions that templates can perform, such as file operations or system command execution. Proper sandboxing helps prevent securities like SSTI. The importance of sandboxing functions restrictions. It limits the functions or methods that can be called within the template, blocking potentially harmful operations. Variable and data access controls access to global variables or sensitive data, ensuring templates cannot be manipulated or expose critical information. Alright, that's it for the room today. We have gone over some basics of the template engine. We also know the basics of SSTI and how to exploit that on different template engines. We have to identify the template engine first before exploiting any vulnerabilities. And then we also talk about some mitigation techniques in protecting your application from SSTI attacks, including sandbox, input validation, and secure configurations of the template engines. If you have any questions, feel free to reach out to me. Thank you for watching. I'll see you next time. Bye.